portion using the telephone number listed in the right-hand panel of your interface under the audio section. Following the presentation, we'll have a brief question and answer period. You may submit your questions at any time using the interface on your screen. I'm happy to turn the floor over to our first speaker, Charles Fisher, Business Development Director, Analytics at Silver Spring Networks. Charles, welcome to the event. You have the floor and should have controls.
Thank you, PJ, and thank you everyone for joining today. So for today's session, what do you hear from us today? We are going to do a Silver Spring company overview, followed by an overview of our specific product stack related to analytics. And I'm going to turn over the floor to Toby DeVilliers, who's going to talk to United Energy as a company overview and some of the recent analytics projects that are in place there. We're going to wrap up today's session with some questions that I'm going to curate and facilitate to Toby around what we heard today. We will allow folks on the call to input questions into the chat window, and I'll be watching and taking down notes and curating that as the session progresses today. So I'm going to start with an overview of SSN, Silver Spring Networks. So we are an IoT network company that has been primarily focused to date on connected utilities and smart city markets. We have over 26 million connected endpoints worldwide, and we have an ecosystem of over 125 hardware and software partners that are integrated at various levels of our network platform. On this next slide, you'll see a map of our global customers worldwide. I think the most interesting statistic here on this slide is the network coverage of over 1.5 million square miles, which is roughly half the size of the continental U.S., with endpoints that are associated to roughly 65 million people, which, to put that in perspective, is about 3 times the population of Australia. In terms of our solution suite, this is a high-level view of our technology stack. We're broken up by lines of business verticals that are focused on the smart utility space, the smart city space, and the enterprise IoT space, where we're enabling new hardware, sensor, and software solutions to get rapidly integrated with our network. Along with this, we have several cross-functional technologies that enable these verticals, and today we're going to focus on some cross-functional analytics capabilities, but specifically for the smart utility vertical. And we're going to dive deep into that on United Energy. So with our customers, the initial use case for an AMI deployment is always related to outage and billing. As our utility partners mature in their deployment, their attention typically turns to a number of other use cases for this data related to grid operations, customer care, revenue protection, demand response, energy efficiency, so on and so forth. So our goal with the analytics product suite here at Silver Spring Networks in the smart utility space is to create a parallel path for AMI data that bypasses the meter-to-cash pipeline for billing and allows the deployment of new data streams and logic without ever having to change AMI meter programming, firmware, or existing enterprise integrations. So this solution set consists of 2 products that we're going to talk about. One is Sensor IQ, which is our solution for deploying grid edge computing and data gathering logic to our network interface card, which is integrated into the meter. And also, we'll briefly touch on the analytics platform, which allows access and democratization of data for new application use cases, as opposed to having folks pulling data out of head-end systems or purpose-built enterprise tools. Today we're focusing in on the Sensor IQ tool, especially with the United Energy case we're gonna discuss. So it's been widely deployed there. This tool allows new data gathering profiles to be created for new data elements off of your existing electric meters, such as voltage, usage, power, temperature, power factor, current, you name it, anything that's accessible by the NIC that's in the meter. The data sampling on the network interface card occurs 5-10 seconds depending on the meter and can be read over the network every 5 minutes. Some of those configuration elements depend on the different meter type and can be faster or slower depending on what's being pulled by the meter. Immediate events or traps and custom logic can be sent over the network for critical events based on the custom defined rules that a utility selects. So here's a very high-level description of the technology and what this product is doing. At the top of the diagram, you have a meter CPU that's reading various sensors and populating electric data into meter tables based on set intervals. So utilities will have configured meter programs to read these tables and gather data on a regular basis via their AMM billing read. So normally after that meter program is set and after you've set integrations with downstream systems, you don't really want to make constant changes on this. Billing and outage are dependent on this information. So this Sensor IQ application enables a lightweight parallel meter data collection path for new data elements or even high granularity data for existing elements. Stores that information on the network interface card for processing, and then we'll either send custom alarms or that data can be gathered at whatever interval makes sense over the network. So this can be deployed and changed on the fly without ever impacting the meter program or read path. So United Energy is a licensed customer for our head-end system and actually is integrating their own analytics platform directly with Sensor IQ. However, for several other customers, we actually are standing up end-to-end analytics use cases on our analytics platform internal that we have here at SSN based on several internal and external data sources, including Sensor IQ data that we're going to talk about today, but also back office systems like MDMS, CIS systems, weather data, business listings, you name it. So this is the technology stack that we're diving into today. But enough about SSN for the moment. So we're fortunate to have fantastic global utility partners who are constantly pushing the boundaries of what we're doing with our network data. A few of these are highlighted here, but today we've got Toby DeVilliers, who's going to talk about specifically what United Energy is doing with Sensor IQ and their AMI data. So Toby has a background as an electrical engineer and is a deep expert on electric and gas distribution planning and protection, AMI and grid analytics systems, and has 25 years in the utility industry. He's previously worked at Elscombe in South Africa, at Mighty River Power in New Zealand, and AusNet in Australia, focused on asset management and network intelligence tools. He is currently the network intelligence manager at United Energy, and we'll talk today about the new solutions that are being deployed there. So welcome, Toby, and we're excited to hear what you have to share.
Thank you very much, Charles, and a special thanks to you and Silver Springs for giving me this opportunity to share some of the nice stuff that we are really doing with Sensor IQ and their smart meters and the analytics that we run on it. So to start off, I'll just give you a quick background of who United Energy is and Multinet Gas. We are Australia-based in Victoria. We are right here in the Bay where Melbourne is. We also, if we look at the blue area, that's our electricity network. The orangey area is our gas network. 660,000 electricity customers, 687,000 gas customers. We are using quite a few of the Silver Spring suite. We've got UIQ, Sensor IQ, ODS, outage detection system, as well as Gridscape. And we've been purchased last month by CKI, so we are now part of the CKI group. That's a very exciting opportunity for us. Belco is also part of this group, so that will extend our smart meter coverage in Victoria to about 1.8 million meters. That gives us really the opportunity to expand on the number of meters that we can do analytics on. If we briefly look at our smart meter population, we had the mandate to deploy smart meters to all our customers. So each and every customer that could get a smart meter got a smart meter. In total, 653,000 of them. We are using the Silver Springs mesh radio communication to all of them. We read them every day. Our daily success rate is 99.83%. So at this stage, the billing data, we retrieve them every hour. The generation that we've got, because we started some time ago with the installation, is actually the slower communication network. So we are unfortunately limited to the 100 kilobytes per second communications. We've deployed Sensor IQ to each and every one of our smart meters. We've put 5-minute interval data on them, and we are collecting voltage, current, and power factor from all of them. Those values are all instantaneous values, so it's not averaged. So we get a time-synced snapshot of what does the network look like every 5 minutes. So that gives a really good platform for any analytics, having that as a snapshot available. To facilitate some of our real-time analytics, we've actually extended that to reading 20% of our population every 5 minutes. So it's not just logged every 5 minutes, but we read them also every 5 minutes. The remainder of them, the other 80%, we bring them back every hour. A small population, a few thousand, we've deployed for specific use cases 1 minute data on, and then in cases where we really sit with a few problems that we're trying to address, we've deployed 10-second data. All those are also coming back every 5 minutes. If we look at our analytical platform, as Charles mentioned, we've built our own analytical platform. So we go and feed all sorts of data, anything that we can really get our hands on, into this. So we bring all our smart meter data in. We also go and take data from our SCADA and our SCADA historian, OSIPI in. The DMS outage data, our asset management system data, the spatial data, and then other third-party data that we've got access to. All of that go into our analytical platform. We are using Postgres with a FutureGrid pre-processing engine to do all the number crunching for us. And then we've got Tableau and a few other presentation layers. We use Network Viewer to spatially represent our data. And then we also go and feed jobs basically directly to the fault trucks through our distribution management system. We issue controls from our analytical platform to SCADA, and we also go and more on the plant side, issue jobs, do assessments of items, and even where we create new master data, we feed that back into SAP, our asset management system. So this project is currently underway for probably about 8 months now. We are in the last 2 months, so in about 2 months' time, all of this will be going alive. Quite a lot of this is already alive, and as you can see from some of the information that we'll be sharing, that's some of the successes we had up to now and where we are. I'll focus today really on what we do with Sensor IQ and what analytics we run on it and the successes that we've got with Sensor IQ. One of the questions I always get is, why are we using high frequency data? And I thought I'll look here at a specific customer. This was last week. The blue is the current that we're getting back from the customer. The orange is the voltage that we are getting back, 10-second data. So we can see the solar customer. It was a cloudy day, so the clouds were coming over and disappear, sun back, clouds. So quite a lot of fluctuation in the solar generation. We can see when the customer woke up in the morning, he did a few things, switch on his kettle, looks potentially like a toaster or a microwave, a few other bits and pieces, a little bit more load during the day, and then in the evening again, did a few things. You can see his fridge also kicking in a little bit later. So quite very fine resolution data. If we take the same data set now and we look at 1 minute data, we can see we still get a really good resolution. We can see there's things happening, but you are losing a lot of data. Well, you're actually losing you only return 1/6 of your original data set. If we take the same data set and look at 5 minute data, again, you lose more and more. Now you only see one peak really in the morning. It's got a little bit of a duration, but you can't now see the granularity anymore. All the clouds and impact that they got on the solar, that is very much disappearing. You see a lot of up and downs, but it's a lot less. So this is for a customer with really quite a volatile load, and this is already the changes that you see on that. If we look at 15-minute data, you again lose a fair amount of the data, and to some extent, if this was not such a volatile load customer, you would have lost a lot of the data. Taking this to 30 minutes, the same, And eventually, if you go to hourly data, that is what your profile ends up looking. So if we throw all of that together on one screen, it becomes quite evident that somehow you need to work out what do you really want to analyze, and based on that, work out what's the best resolution for your data. We all want 10-second data, but we can't necessarily afford to bring all of that data back. If we look to go from 60-minute data to 5-minute data, it's 12 times more data that we need to bring back. Very similar, to go from 60 minutes to 10-second data is 300 times more data. And that's not just 300 times more data, it's 300 times more data on your comms network. It's 300 times more data that you need to process and analyze, you need to store it. So overall, it's got quite a big impact on your system. And typically everybody's worried that the moment we start to talk 5-minute data, we're going to break the systems. And we do. And it's important to work carefully through all these things and really look, are we going to break it, carefully move forward and make sure we are not breaking really too much of it. When we started off, and this was about February 2016, we started off with reading our 5-minute samples on the whole network every 4 hours. We very quickly cut over to reading them every hour. And this was a histogram of what we've experienced bringing the data back every hour. It's about 200,000 records that come back every minute. Every blue bar represents a minute. And the data all landed in about 15 to 17 minutes. And you can see the hourly peaks, fairly high peaks, and then there's actually a lot of nothing happening. And that was where we're starting to look at what's happening actually if we bring now the data back more frequently. And the same happened with the 4-hourly data, where it was actually far higher peaks, and then 3 hours and 40 minutes of nothing happening out there. So that's really a poor utilization of a communication network. And that was where we started to look at bringing the data back more frequently. So with 20% of our population coming back now every 5 minutes, we've actually dropped our peak to only run at 70,000 per minute, but it's now quite nicely equally spread. We don't see those big dips anymore. If we zoom a little bit further in, we see there's still a few dead times that it's not that it is a constant load now, but every 5 minutes, on the 5 minutes, we poll for the data. The data start to arrive on the 6th minute, more data coming in on the 7th. By the time we get to the 8th minute, it peaks and then start to drop off. And the last few slow ones come in on the 6th minute, basically just at the same time as we go and do the poll for the next one. So 20% of our population go and we land all of that 6 minutes after the interval is expired. And that really becomes great for our near real-time analytics. To show you some of our use cases and what we are doing with the data that we get in. If we look, this is our electricity network, and this is our spatial tool that we use to represent all our data. If we go and choose here a few of our layers, we've got here a layer that we put all our smart meter data on. And if we, for instance, turn on average volts, this gives us a very quick heat map of what does the voltages look like on our network. And we can turn on the legend. And looking at the legend, you can see here green everywhere where we've got a little bit of green. We've got probably a little bit of close to undervolts, everything where it starts to get to orange and red. We've got a little bit of an overvolts issue. So we can go and zoom in on any area of the network and see, ooh, here's a few orange spots. We can zoom in a little bit closer on some of these orange ones. And as we zoom in, we can clearly see it's very specific clusters that highlights that this is potentially a very specific substation that sits with the issue. If we go and turn on our low voltage network, enable the GIS data, low voltage, that go and show us the extent of the network, and that clearly show that it is most likely all one substation. If we turn on our network trace, and so we run that from let's say from there. We can see all the customers on that substation, and yeah, that's indeed all the orange ones. All of them sit with overvolts. This very clearly highlight that we've got an overvoltage problem or potential overvoltage problem in this area. It's one of the highest averages on our network, and it shows us this is a transformer potentially earmarked for tap down. We can now use this information and build really nice dashboards for the planners, looking at which substations are the biggest priority, the highest volts on the network, the lowest volts on the network, and they can use this for providing their capital plan and input into their planning for the next financial year. Some of the other nice features that we've deployed that I thought is probably it looks nice on looking at the high voltage one, that makes it easy, is if we turn on our cross-referencing layer. This is something that go and tell us of where analytics ran across the network and identified places where we think these customers are most likely not on this transformer, or adjacent customers are actually on this transformer. So we see there's an open point, we've got another open point, so those customers are all very close to open points. We quite frequently see that our customers are connected to the wrong side of an open point. Analytics now help us to confirm that. Very similar with this one. It's a customer close to the open point, most likely wrong. If we look at the voltages, as I say, with this being a high voltage substation with low voltages or relatively low voltages around it, makes it very easy to visually see that, well, that one's voltage look very much like these ones. Those three look wrong. They look very much like the other two. And this one, yeah, that one's a little bit more dicey. But a really good visual indication that this analytics must be right. If we look at this one's a bit of an odd one. It's not connected to an open point. And we start to wonder, well, what's wrong? Is this one now really right? Analytics tells us it's wrong. What happens here? If we go and use Google Street View, and we can just go and zoom in into this area. So Google Street View shows us that street, and we can see, oh, yep, it looks as if there's a line running across from the open point to the boundary. If we zoom a little bit further in, yep, it confirms that. So if we look at the street name and we go back, we need to go back in the right direction. So we can see that property indeed is being fed from the open point there, and we've made a mistake. It's not connected to this pole. It is actually connected to this pole, and it's on the other side of the open point. If I turn on our inspection layers, we bring all our inspection photos also back into our spatial tool. So every inspection photo that's been taken over the last 3 years, and we've got about 300,000 photos in now, is visually represented here. We can go and click on the inspection photo, and that brings up the photo that was taken. This one was not taken that long ago, and we can explode this and zoom in into the fine detail of this photo. It's all high resolution photos, and this may even help us to see where the lines are connected, and this really is a good tool for us to use to just visually, without having to send anybody out into the field, confirm where they are connected. We also sit sometimes with our cross-referencing with cases where we sit with a meter, in this case, that it just doesn't belong there, but we also, it's not close to open point, we cannot find its mates. So what we've done is we were starting to do signal strength analysis, and this meter communicate to all these meters that's about 30 kilometers away, and say, well, that's a bit impossible. So all its mates sit in this area. And looking at the signal strengths, we could clearly see who can it talk to, what is the signal strength of the meters that it talks to, and we could work out that meter is actually in this area here. Now, using the voltage profiles, we can, to the closest 50 meters, actually pinpoint exactly where that meter is installed. So we can confirm it's not installed there at the coast, it is actually installed, and we can pinpoint the property where it's installed. So we can send field crew out and actually get the information from the meter. We had similar cases with lost paperwork. We sit with meters providing data. We've got no idea where those meters are coming from. This actually helps us to identify where are those meters installed, trace them back, and get them into the system. We've identified 9 stolen meters this way, where somebody got somehow hold of some of our smart meters and installed them as check meters to a few tenants in his house. And using this method, we actually could pinpoint and found these meters sitting behind his fridge, or measuring every room in his house individually. If we look at some of the benefits and so on that we've got with this, it's really delivering good benefits for us. We need to notify customers of outages on the network. This helps us to tell us really which customers are going to be off. If we send them SMSs, we send the right customers SMSs to tell them when they expect their power to be back. If we do load aggregations, we can now go and make sure that we submit the correct customers to a specific transformer, and at least ensure that we get that right. It's of no use submitting all the loads together and we think we've got a good answer, but we didn't submit the correct customers. Another big use case that we're running with is identifying what phase every customer is connected to on the network, or every load on a 3-phase customer, which one of the 3 phases that load is connected to. So again, going to our spatial tool, and if we go to phase data, and if we switch on the substations, we've created pie charts for all our transformers on the network. So we can clearly see how good balanced they are. In some cases you see with some where everybody's connected to, or big portions of the customers are connected to the red phase. If we want to zoom in on a specific area here, we can go look into that area and we see, yep, looks like about 50% of this one is on the red phase. We can go and switch on our individual customer phase data. So we see there's a few 2-phase customers, there's a 3-phase customer, a few single phases. Red, quite a few customers on red. We click on the substation, it actually shows us that, yep, the first phase set with 27, it's almost double compared to the rest. It also shows us how many customers are connected. Now from here we can go and drill through and look at the specific loads on that one. We don't have any measurements on the transformers itself, but with all the smart meter data coming in, we can now go and plot each and every customer's voltage on that transformer, and we can see what do their voltages look like. Here we can see one that is potentially again incorrectly mapped to that transformer. It just does not look like the rest. And we can also go and submit all our 5-minute data. So we can now save a lot where we don't have to put monitoring on the transformers. We can just purely go submit all the data that we've got, and we get per phase good information of what's happening on the transformers. And from here we can go and build dashboards for the planning people. We can look at what's the unbalances on phases. A lot of times we sit with a single phase that go and blow a fuse on the transformer, causing outages. We never expected it would be, because the loads look quite normal on a transformer. And all of this is now done automatically. It runs gradually through the network, and we can come up with dashboards telling us which ones are the ones, again, priority-wise to address and sort out. What we also sit with is, a lot of times we want to do augmentation. They go and just connect the customer to the closest phase. By looking at our loads, we can work out which customers are actually on what phase, and then any new connections, make sure if it's need to go into the blue phase, we make sure new connections must go on the blue phase to balance connections out. Quite frequently we see that damaged transformers are caused by a single phase. Total load on a transformer is fine, but you sit with one single phase, and that single phase is overloading your transformer. This is one of our other use cases. that I've got the video here with a histogram of how many customers are reporting what voltage on the network. The green block is our compliancy, where the distribution code sort of limit us to customers should not be lower than this or higher than that. And we can see we already sit here with some customers higher. This was a very specific hot day that we had. And if I play the video, you can see how this is the 24-hour period. In the small morning hours, we were really sitting with a lot of customers non-compliant. We see on top here the temperature. As the temperature starts to increase, it's going up to about 100, 107 Fahrenheit. We start to see here a fair amount of customers actually undervolts as well, going as low as 5%, even 10% under. Then a cool change came through and the temperature dropped and we sit with, again, customers over. So the planners need to go and design our whole network to the maximum volts to make sure everybody get on hot days also a good voltage out. So that causes all sorts of issues. It's not a dynamic change. What we've built now is we look at the smart meter data and we feed the smart meter data into our analytics, and that 20% real-time data, we are busy feeding that now back into SCADA and tell SCADA, well, this is what the network currently look like. This is what the customers experience. So this is not what we get from our high voltage measurements. This is truly what the customers see. So if we can go and we can shift this with 3.5%, we can drop the volts in real time 3.5% and everybody starts to become compliant. We can also decide whether we want to control. If we want to control to the middle of the line, we can drop it 5.5%. Or if we want to do voltage conservation, we can use the same algorithm and just control to the low side. So we can get away here with dropping the voltage 7.5%. To give us more control, we can now focus on these customers on the shoulders and actually look, these ones, if we just tap them a little bit up, we can actually have a lot more flexibility. And similar on this side, if we tap these customers down, we narrow our histogram and giving us better control. If we use Tableau, we can focus on those shoulder areas. We can clearly see where are those customers, and we can see they're all clustered together, pointing that it's a substation or transformer, a specific transformer. By just tapping that transformer a little bit higher or lower will give us a lot more control. One of our big successes is the work that we've done with our detection of neutral issues on customer premises. This is a typical household, so we sit with our transformers that is earthed, and we sit with a house that is also earthed. We sit with a live and a neutral coming to the house. The big problem that we've got is the moment something goes wrong with a neutral, we sit with a live, a good live to the house, and then we sit with current going back through earth that is high resistance, and we start to get high voltages, reasonably high voltages at customers' premises that can cause shocks. So we started to use the smart meter data not just to measure the consumption inside the house, but also use that as an analytical tool to measure backwards into the network and actually measure the quality of our service main to the house. And we can extend this to three-phase customers as well, so both single-phase and three-phase, very similar issues. Now, we were quite unlucky in Australia. We had a fatality in October last year. That was the result of a neutral issue. There's so far 3 known cases of neutral problems that caused shocks to customers, and yeah, it's a very unfortunate situation that we had 3 deaths over the last few years. What we do with the smart meters is we actually use that to measure the impedance back into the network. And as a result of these historical deaths, we are forced to go and inspect each and every property. They use a neutral service tester that just purely go and it's a pass or a fail. That go make an assessment. If the resistance to the house is bigger than 1 ohm, they fail it. We've used that same principle with our analytics and basically say, well, we can accurately measure the impedance. This is a histogram of all our impedances, typically about 0.2 to 0.25 ohms. Every one over 1 is a fail, and we started to dispatch that to the fault trucks. Also very similar, we can do now a risk assessment and see how bad is it and what's the chances of a customer getting a shock. So we overlay risk matrices on top of this and issue all those ones. That depends whether it's an urgent job or not. Here's a few cases of customers that was just, the neutral just pulled out, no neutral at all. We sit with a lot of corroded terminals that result in very high resistance connections. Burn through connections, insulation breakdowns. There's a vast range of things that go wrong. If we look at our Australian standard, it was calling for any protective device and so on in the house that if we reach a touch potential of 50 volts, it should actually go and disconnect the supply. We started to use the same principle on the house assessment, and we are in the last few stages of implementing this as well, that the moment we sit with a 50 volt touch potential, we can actually use the smart meter and issue an automatic disconnect from the analytics. We've already developed this code and it's just going through the last few phases of testing it. Also similar, if a customer severity reaches a certain point, we can go and electronically dispatch this to our DMS system and out to a fault truck. As a result of the work that we've done, we've managed in 2016 to reduce our average shocks by about 50% compared to the trend that we had over the last 5 years, the average for the last 5 years. If we look where we are so far in 2017, we are doing good. We started off really good, and then we are averaging at this stage almost similar levels to last year. We hope when this whole thing goes into full production and everything automated with the jobs getting all electronically issued, that we can probably halve this again and probably end up with a quarter of the original jobs that we had. What we've also noticed is that if we look impedance on the Y scale, that the impedance sometimes go and creep up over time, and this is over a 9 month period. So we can see the network impedance, we got worse, we fixed it, and after that it settled back to, in this case, about 0.3 ohms. So this, in some cases, was a good indication that problems are not all a snap and something goes wrong, but we can pick them up over time and actually start to plan for it. This was a case of 3 houses, all supplied from a single pole. And if we take the average of that, we see a very similar pattern, all was good. Something happened and probably resulted in a bad connection. It got corroded and got worse until we issued the job, and then it restored back to normal. With this specific case, we had mixed success rates where sometimes we send the fault crew out, and unless they can really detect the problem, it's sometimes hard for them actually to find it. So we are at this stage looking at options of how can we work with them and train them up better, get them the right equipment that we can actually proactively fix these problems before even currently a fault truck can detect these problems. Last year we've detected 1,200 cases. All of those ones were proactively fixed before, almost in all of these cases, before the customer actually noticed there's a problem. So we arrive on site, we are there to fix their problem. A lot of times the customer denies that they've got a problem, and once we show them, they're actually quite appreciative that we came out and fix it. Our algorithms are at this stage running on a 98% success rate, so very few ones that they can't find. If they can't find it, it's most of the times a case where we send them back a second time and they find it on the second attempt. So we can now save, instead of having to go and do all these inspections on a high frequency rate, sometimes 5 year, sometimes 10-year inspections, we can do this remotely. Every hour we run the analytics across it, and typical detection time to confirm it is about 4 hours. So instead of waiting 10 years, we can now go and within 4 hours go get the fault truck out there and fix it. Very similar to the case I just mentioned, one that we can go, analytics that we've developed to detect backbone issues. Everything that's blue means that the network is fine. Green means, yeah, there's here and there slight issues, nothing serious. Yellow, orange, and especially red means there's something that we need to attend to. So we can see there's a case in this area. If we zoom in there and we switch on the LV network, we can see all these customers are feeding off a specific spur, except those two. So those two sometimes go and you raise your eyebrows and say, well, why are those two now also indicating a fault? Again, if we zoom further in with Google Street View, we can see, those two properties are feeding off the bottom cross arm that's the same as all the other people across the street. So everybody feeding off the bottom cross arm's got a problem. Everybody off the top cross arm is fine. And time and again, we sit with just having to go there, replace the connections on between the two cross arms. It's just a jumper, a bad connection on the jumper between the cross arms, and about 80% of the time it's due to a neutral jumper that's causing all these issues for us. We go, we fix that, and the problem is gone. So this saves us really a lot of times, a lot of money for the fault trucks. It's sometimes a specific customer that complain. They go, by the time they get there, the problem is not there. They investigate it, they try to fix everything for that customer, but the problem's not with the customer. The problem is sometimes 300-400 meters away elsewhere on the network. And because one customer complained, the fault truck only attend to that customer. So analytics really help us now to sort that out. We can go and identify those issues very quickly and send the fault truck to the right pole, and they get that fixed. And again, all of this is happening now every hour. We get the data in. We sit a lot of times here with big swings on the voltages, damaging customers' equipment. We sit with claims coming in as a result of it. And going and taking that to the extreme, it goes sometimes right down to a transformer. Something goes wrong on a transformer. Yeah, it's burnt neutral, the neutral burnt off. The specific one at the bottom was an internal fault on a transformer. And all these ones were proactively identified before any customer called in. We could actually pick up with a smart meter data, something is busy going wrong on site, and get that actioned. So again, this helps us to prevent claims. We sit with big voltage swings. Some of them go sometimes as high as 300 volts. That is about 20% over volts. It go as low as 20% undervolts. Yeah, it can't be good for any equipment. Another use case that we've got, this is the last one that I'm going to cover and we'll have time for, is our theft detection. We sit with meter bypasses on the network, and a lot of people go and tap in before the meter. So on the way to the meter, they make a hole in the wall and they take supply from it. They are very clever. They still run a big part of the house through the meter, so it looks like a normal house consumption. A lot of our normal methods of detecting bypasses or meter theft just does not work in these cases. Below is a sample of a thermal camera of one of these crop houses. That it's just full of marijuana. We pointed to one of the windows and got, this is about 60 Fahrenheit that we got back from that one. We pointed it to the outlet in the roof and we got from that 130 Fahrenheit back, really indicating there's something seriously happening in that house. If we start to look at some of these bypasses, people go, they just cut a hole in the wall on the way to the meter and tap into it. There's a few examples. In this case, they actually broke into the brick, removed some bricks and just tapped there into it. This is a case inside the roof. So these are underground. This is an overhead. So the line comes from the street onto the roof, in the roof, and in the roof they just go and bypass it. This one was quite blatant. He actually did it on the outside, quite visible from the street, that he went and bypassed his meter. If we look at what we found inside the house, this is a typical setup of what they are doing, all the ballast that they use to power the lights. It's a fire danger. You just can't believe once you see these things. This specific case is a pantry, and just how they fit out the pantry and all the electronics and stuff that they run in there. It's incredible to see. What we see in the rest of the house, a lot of times we see lights, heat lights that they run on cycles, 12-hour cycles, sometimes 9-hour cycles. Depends on the age of the crop, 24-hour cycles. And yeah, it's using a lot of electricity and a big impact on our network, and it's all unmetered. Here the guy was actually drying his crop as well. He harvested it, and he went to the next step and actually dry it as well for sale. These things are all fire dangers. These are just purely on our side of what happened as the lines were coming in on the point of attachment and on our FOLCB. On the fascia board, burnt out. This could have just as well spread into the house and actually caused the fire. So with the analytics, we can monitor now all these things, really pick up what is not going through the meter. And we've made a really good assessment on this, and we've got it now down to a fine art where we can actually measure with the SensorIQ data the amount of energy that is not going through the meter. We even had cases where we could go and detect the customer that didn't have a smart meter, because just by the analytics that we could do on the adjacent meters was dobbing this one customer in without the smart meter, and that helped us to pinpoint this customer that he was also actually a crop house. So we found about 150 cases so far that is under investigation that we are busy working through with the police. As part of this, we've also identified about 160 incorrectly wired meters and faulty meters. That is stuff that wasn't really that possible with smart meters, without SensorIQ data. So having the voltage and current data really helped us to sort this also out. So this is just a few samples of our use cases and what we've got time for. We've got in total about 22 that we are busy working through, but yeah, thank you very much for the ability to share this information with you and just telling you of some of the nice things that we are currently doing with the smart meter data, and specifically the SensorIQ data.
All right, great, Toby. Thanks. Always great to hear that. So I've got a few questions that folks have been populating in the chat window, and feel free to keep adding those as we're going through the Q&A session that we're going to move into right now. So the first one that came up, so was the 20% read at 5 minutes, the 80% at 1 hour driven by a technical constraint? And I'm going to add in a couple comments here, Toby, and then turn it over to you. So for Unite Energy specifically, they are currently on our Generation 2 and Generation 3 devices from the network side, and on the I think Generation 2 of our SensorIQ application stack. So our Gen 2, at least our Gen 3 devices run 100 kilobits per second on the network and have about 4 megabytes of memory. Our current generation Gen 5 devices, which we're on, have 24 times that, with 2,400, up to 2,400 kilobits per second data rates and up to 32 megabytes of memory. So one constraint as you might be rolling this out is just network bandwidth. We've designed our network forward-thinking with plenty of bandwidth, which is proven out by the use cases that Toby and team rolled out. But we've significantly increased that in the hardware in later generations. And on the application side, the current version that United Energy was on, the application side scaled up to in the hundreds of thousands of devices, and Toby and team pushed this thing to its absolute limits, which was great. And our current version that we're on scales to 6 million devices, especially through some of the learnings of working with customers like Toby. So the idea here is that as you're rolling this out, you need to make sure you're taking a measured approach and moving out the read jobs, moving out the intervals, taking stock of where everything's performing, and then continue to roll out more and more aggressive schedules, which is kind of the phased approach that UE took with doing some of this. Is that right, Toby? Is there anything else you want to add to that, or are you guys looking to further move your read jobs at all, or anything you want to add there?
No, I think you've nailed it. It's really, as you go and do these things, you are breaking things. I am still pushing the limit that I want to go more than 20% and ideally the whole network. We are looking at upgrading to your new SenseIQ 3 that will give us that scalability. At this stage, we sit, I think, on the existing version of SenseIQ. We've probably reached the limit on what we can do. We need to go to the next version if we want to go more than 20%.
Mm-hmm.
And I think the main aim is billing data. We need to protect our billing data as well. So billing data is the most important thing. Once that is out, we use whatever bandwidth is left, and we are.
Yep, so the idea here is with our existing customers, we take a very measured approach with rolling this out systematically and stopping and making sure that we're watching how the network's performing. With new customers that are on the latest technology, the sky's the limit. Okay, Toby, the next question on this was, how long did it take to set up this analytics system? And I think this might be a little bit of a loaded question because I don't think you ever stop setting up new things, but any input on that?
Yeah, it can be a very long answer. I've built a lot of this in a previous life with another utility before, and I started with United Energy about 3 years ago with the aim of setting this analytical platform up. So it took us probably the best part of 2 years to just work out how are we going to do it, what's the platform we're going to run on, and get the business cases and everybody across the board that, yeah, we definitely need it, why we need it. And once we've got that approved, it was really running very fast. We've worked through a few proof of concepts and we've decided to use Postgres, and that project's now running for about 8 months, and we are probably about 2 months away from having everything completed, all the interfaces automated, and just everything working. So I would say from the moment the business case was approved, it's probably going to end up being an 8 months project.
Got it. So Toby, there's a question here around the image that you had on there. How did you get the inspection image of the tie point? Was that a drone, a guy in a bucket? Where did that come from?
Okay, what we do as part of our inspections, previously we were just doing ground-based inspections with a guy standing on the ground with a camera, and we found that a lot of times our cross arms look totally different from the top than from the bottom. And then people started to come up with all sorts of innovative ideas of putting a GoPro onto a link stick and put the link stick up there, and they started to get all fancier and fancier. So currently it is a camera mounted on a link stick with Wi-Fi. They can see on an iPad or something else that connects to the camera what they actually see on the GoPro or the camera on the link stick, and remotely control the camera. So it is basically a link stick mounted camera with remote control. And we do all our inspections now that way. Take high resolution photos from the ground, put the camera on the link stick, and take 1 or 2 photos also from the top.
Okay, so we got a question about, does the meter and sensor tech have the capability to measure usage by different devices at a home or business, like an air source heat pump or an EV charging station? So I'll answer that one. Yes, it does. So Zigbee connected devices can be pulled by the sensor technology to get data elements off of them and custom alerts and alarms off of them, similar to the way this device is pulling meter data tables. So our network interface card has a Zigbee radio, and connected devices can be pulled in a very similar way. So another question to you, Toby. Is United Energy hosting the data at the utility?
Yes, that was one of the big debates of where we should put it. The main reason why we decided to host it locally was with our real-time analytics. With us taking control of SCADA, that's a security risk as well. So we do not want to go and have a cloud interface directly into our SCADA system. And our advice at this stage is that also, if we really want to go real time with these big data volumes, that we will most likely struggle with a few delays. So therefore, we are hosting at this stage everything in our own data center.
Okay. Next question. So how exactly are you measuring the unmetered consumption on the bypasses? Does that question make sense to you, Toby?
It does. I don't want to give too much IP away, but I think what it's really coming down to is every load that you switch on the network has got the impact. So if we go and somebody switch a big load on like a crop house, you do see a voltage drop. And then with all the other analytics that we do, we know what the impedance is of every supply point. So it becomes a very straightforward calculation where your power equals your voltage times current, or V equals IR. With your resistance, if we know what the resistance is and we know what the impact on the voltage is, we can actually go and calculate the current. And therefore, yeah, you just need to have the smarts to be able to calculate your impedance and the other factors accurately. And based on that, you can calculate your current very accurately.
Well, Toby, there's a really key thing that when you and I were discussing this earlier, it dawned in my mind, that's important to this is, you know, so when we're getting this data off of the network, the fact that we have all of these devices that are, they're syncing back their time with our access points, so they all have good time synchronized information, and they're time stamping all of these reads and storing them locally and then pulling them back on a regular basis. So as opposed to like pulling these things from the back office, you're getting good time stamped data to get that snapshot and compare against. I mean, that's, as an input to this kind of stuff, is relatively important, especially when you're comparing across several devices. Is that right?
Yeah, I think the moment you want to go across a whole transformer, it becomes really critical to get those time shots or time snaps really accurate. For a single custom analysis, you don't really care. The frequency is the frequency and you use the data. The moment you want to go into the nuts and bolts across a transformer, work out where's the problem or who caused what, you don't want fluctuations where the moment your data is not properly time synced, there's lots of different variables that comes into play of other people switching loads on or off during that time mismatch, and it makes your analytics a hell of a lot harder. So having a single time shot, accurately time sync data, and the more frequent data really makes your analysis a lot easier, and all your algorithms and everything just runs a lot smoother.
All right, so last question, I'm going to turn it over to PJ to close. So how do you identify the phases on each distribution transformer? You can easily group the data into 3 distinct groups, but how do you match one group to the red, white, and blue, or the 3 phases, right? Is there another meter at the transformer? That'll be our last question.
Okay, we don't have any meters on the transformer, but we actually take that same sort of analytics and move that one level up, going, again, not giving totally all the way, but we go right back to our substation, in our case the zone substation, and we pick up from our zone substation what red, white, blue there is from the circuit breakers, and we do that matching from high voltage all the way right down to the individual transformers to work out how the low voltages reflects onto the high voltages, and that gives us a really good view of what red, white, blue is on each and every customer across all the different transformers.
So effectively aggregating this data up to parts of the distribution connectivity model.
Yeah, not necessarily aggregating, but running the analytics across high voltage and low voltage all together.
Gotcha. Okay, PJ, I think we've come to the end of this, guys. Any open questions? We will work on responding to as many as possible. And thank you so much for your time. PJ, I'll turn it over to you to close us out.
Thanks, Charles, and thanks, Toby. Fantastic presentation. For our audience, we hope you've enjoyed today's discussion. As you log off, please take a moment to complete our survey and give us your feedback so we can continue to provide you with quality content. Thank you for attending, and this does conclude today's presentation.